All right, good morning. Did lab three go okay? Turned it in okay? Yeah. So if you are late on lab 3, then you have until next Wednesday to get it in and still get some points for it. You can also take a late day if you'd like, but you can only use that on one single assignment. Cool, okay. If you need help on homework or on lab 3, there's office hours today, and highly recommend that you go to them because the sooner you fix your bugs, then the more points you're going to get. So yeah, try to go to office hours today if you have not finished lab 3. Okay, midterm is on Wednesday of next week. On Monday, we're going to have kind of like a review session, Q&A section. I'm going to make a Piazza post where people can respond to the Piazza post with all of their questions that they have. And I'll publish a list of topics that the midterm will cover. Most importantly, so the midterm is going to cover homeworks 1, 2, and 3, with an emphasis on homeworks 2 and 3. And it will also cover things that we've done in lecture and things that we've done in lab. Hopefully you have good notes and things that you can review. All lecture materials will be posted today. Sorry that I haven't posted this week's lectures yet. Been working on that. So I'll post all the lectures today. Yes, so hopefully you all do fantastically on the midterm. I'm assuming all of you will, you'll do fantastically. I'm assuming that the people who skip class, those are the people that maybe won't do as well. So I have complete faith in all of you. But with that said, yes, so please think of questions that maybe you're unsure of certain things that we've talked about in this class. If you have any questions, please put them in the Piazza post that I will make a Piazza post, reply to it with a question you have, and then on Monday I will go over all of the questions that you have asked in the Piazza post. Okay, cool. So this very reasonable sort of midterm question. So given 2 register file addresses, output the product of the data stored at those addresses. Okay, so we know we're going to have probably a register file. And the register file is going to take in 2 addresses and we'll spit out a read port and then another read port, and then we'll multiply them together. Let's draw that out. So first, we probably have, register file, and I'll call this register file. And this takes in 2 addresses. So I'll call this address 0, address 1. Okay, and then this will produce data 0, data 1. And then after that, then that is fed into a multiplier like this. And then here's the output. Okay, this is great. But now maybe I will say okay, so assume a bunch of different timings for a bunch of different cells. So inside of this, maybe the mux2s take 500 picoseconds, and also the clock to Q is 400 picoseconds. And is that all that we need to figure out the delay through this register file?
Size of the
I think so. What was that?
Size of the register.
Sure, yeah. Good point. So the register file, maybe let's assume that this stores 64 words. Okay. And then for this multiplier here, so what was required to implement this multiplier, given what given how we implemented it a couple of days ago? What do we need? Yeah.
We did the bit multiplication thing where it's the select line is one of the numbers
Yeah.
sequentially, and then the other line is just the number, but then you bit shift it
Yes.
left.
Yes. So we're going to have a mux of whether or not we taken either a 0 or we've taken that value shifted. And we do that for all of the different bits in probably our second input. But then what do we do with all of those outputs from the muxes?
Add them?
Yeah, exactly. Now we add them. Okay, so let's assume that our add, and maybe this is a 2-word n-bit adder, so maybe it just works for whatever width that we're going for here. Maybe it's all 8-bit words. So our adder takes maybe 5 nanoseconds, and our mux2 is still 500 picoseconds. Okay. And then maybe for the final thing, maybe let's assume that this output is actually being outputted from a flip-flop right there. Okay. If this is the case, then now we need to, of course, think about setup time. So let's say that setup is maybe 300 picoseconds. Okay. With all of this information, you should now be able to figure out the delay that it takes to go from these addresses into this flip-flop. So I want you to go back in your notes, spend like a minute thinking about this, and we'll go through kind of each step of how to figure out the delay through each one of these steps. And then we will kind of continue building upon that idea throughout this class. Okay, yeah, so go and review your notes. How do we implement this multiplication unit? How do we implement this register file? Figure out the delays given this size, and yeah, maybe this is, I guess I need to specify the bit width. I'll say this is, let's say 64 bits as well. Okay. For the register file, so if we have 64 words within our register file, then what is our address width going to be? Like, what are the widths of these two buses? I think it's 6, yeah, because we have 2 to the 6 equals 64. So in order to address into the 64 different possibilities, we need 6 bits. So each of these, I'll just quickly write that out. So this is 6 bits. Okay, and little hack for you. So with the register file, remember, so it's like a big array of flip-flops like this. And then the idea is then we have a big mux tree after that goes pair at a time, pair, like comparing all of the pairs, and then it converts it now into a list of outputs that are like half the size. And then after that, then it does a bunch more comparisons, and then it'll convert it into another one that's half the size, until finally at the very end, now it will just be one single output. And the select bit on every single one of these, so in every column, the select bit is actually going to be the same on each one of these, right? Because we're hoping to like reduce it by the same kind of level. So the select bit is going to be the same. And if there are 6 different select bits in the address, then that tells us that there's going to be 6 different levels of muxes. So if you're ever wondering like how many like if you have this mux tree structure where you go from like a large number of inputs, how do you now reduce that into just one, like funnel that into one single output? Then the number of levels of muxes will just be equal to whatever your like select width is. So therefore, if we have 64 registers, then how many levels of muxes will we have?
6.
Yeah, right, we will have 6. So if we have 64 levels of muxes, I'll write that out. 64, then that means, and that means that then we have 64 inputs into these muxes, right? Then in order to convert it all the way into one single output, then the number of levels will be 6, okay? And if the number of levels is 6 and the delay is 500 picoseconds, then how how many nanoseconds does it take for the signal to propagate all the way through just these muxes? Maybe let's ignore the registers. So how long will it take to go through 6 levels of muxes at 500 picoseconds? Yeah. Go and shout it out. 3 nanoseconds. Cool. 3 nanoseconds. Yeah. So that means that, and altogether, this is 3 nanoseconds. But then we add, what delays here? From the flip-flops?
700 picoseconds?
So remember when we are reading from flip-flops, so we're not actually writing to these ones. So we don't care about the setup time because like we're not even writing to them in this circuit. We assume that maybe something else is having to worry about the setup time. So yeah, so what is the only delay that we need to worry about in this case? Yeah, it's only clock to queue, because that's the only delay that is associated with the output. Yeah, so therefore, we have in total, what is this full delay right here? Cool, yeah, 3.4 nanoseconds. So therefore, this delay right here, and on this register file, maybe it would make more sense if I add a little clock input just to really denote that there's going to be a clock signal here. So this whole section right here from the clock pulse all the way to generating data is 3.4 nanoseconds. Okay. And we can do something very similar for the multiplication unit. Yes, question?
Oh, nanoseconds. Never mind, sorry.
Cool, okay, yeah. Okay, so then for the multiplication unit, so how do we make a multiplication unit again? Like what's just the structure of it? Yeah?
So you take each one and you take the input and you shift it, and then whether or not you add it is based on if this bit is set unlike the other.
Right, yeah, I mean, so we're gonna have, a bunch of muxes, and then we're going to have a bunch of adders. And I guess that's what I was kind of thinking of, is it's basically like the exact same structure as here. So this, I will just make clear, this is what a register file looks like. Register file, specifically the read port. And this is very similar to a multiplication unit. Where we have some sort of like initial cell right here. And we can assume that probably the shifting just happens like immediately. Maybe the shifting is done with just like, just the zeros already exist. Like we maybe don't have like a dynamic shifter attached. So then we have like 64 of these muxes now, because there are 64 different bits that we are feeding in for the select. So this is this is data 1 0 0, and then this right here would be data 2 0, or sorry, data 1 1. Thank you. Yeah, and then this would be data 1 2, and all the way up to data 1 63. All the way up. So boop boop boop, and then data 1 63. Yeah. Okay, good. And then we will have a bunch of adders coming out of this now, because now we need to add up everything that comes out of these muxes. Yeah, either it's 0 or it is the data 0 shifted by whatever the place is of the mux. Okay, so then we have a bunch of adders. And how many logic levels of adders will we have if we have 64 inputs? Yeah, it's still six levels, right? Yeah, so this will be number 64, and then this number of adders in a line, number of levels will be 6. Okay? Good. So that means that now if our delay was 5 nanoseconds through the adder, but then our muxes are 500 picoseconds, then what will the total delay of this whole circuit be? What was that? Right, so I'm assuming that shifting takes 0 time, because maybe, yeah, it just happens automatically in the muxes, yeah.
Something like 5 times 6 plus 64 times the other delay?
Right, so actually, I guess I'm saying that let's just ignore this other delay. Yeah, so it would be 5 times 6, and then probably plus 500 picoseconds, because that would be the delay through all of these muxes. So it's 500 picoseconds all together, because they all happen in parallel, plus 6 whole levels of adders that each take 5 nanoseconds. So in total, this whole delay, I think, will take 30.5. Sorry, 30.5? Yeah. Yeah. But then notice, right, it goes into this flip-flop. So what additional delay do we need to add to this now to incorporate the flip-flop timing? Which delay matters in this case? Is it clock to queue or is it setup time? Yeah, well, it only cares about setup time in this case, because we're not looking at what is going to happen on the next cycle. All that we care about is just this single path from this flip-flop to this flip-flop. So we don't care about what happens at like the next endpoint. Yeah, so in this case, we'd only care about the setup time. So in total, actually, I'm going to rewrite this a little bit, and I'll say that in total, including the flip-flop timing, then now this takes 30.8 nanoseconds. That'll do. Sorry. Okay. Okay, great. So now let's add these two values together. You'll see why I separated them in a second. So if we take, 3.4, 30.8, what is the sum of those two? Yeah, so in total 34.2 nanoseconds. And what does this number tell us about the clock? What is this? Okay, tell the person sitting next to you, what does this delay tell you about the clock signal? The clock that goes into the register file and the clock that goes into this flip-flop. Okay, tell the person next to you. Yeah. Okay. Any volunteers? What do we learn about the clock from this number? Yeah.
Can the clock cycle not be less than the 34.2? So it's like 35?
Exactly, yeah. So the clock period, the clock cycle, the length of the clock cycle cannot be any shorter than this. The time needed for all the data to propagate through is exactly 34.2 nanoseconds. So if we were to shrink our clock pulse to happen a little bit faster than this, then the data wouldn't properly propagate all the way through, and we would have a timing violation. What timing violation would we have on this flip-flop if our clock period was less than this? Yeah.
Setup time?
Exactly, yeah, we would have setup time violation, because if the delay, took a little bit longer to arrive, then we wouldn't have set up our flip-flop properly. Yeah. We don't want that. So therefore, this is the minimum possible clock period. Okay, let's convert this now to the maximum clock frequency that we can have. So feel free to pull out a calculator. You will not. I haven't decided whether I'll allow calculators on the exam. I think people enjoyed having calculators last quarter, but it just means that I'll have like grosser numbers like this. So it's like a trade-off. It's like, do you want pretty numbers that you can just like, it's like, you know whether or not you got the correct answer because it's like very easy to work with, or do I give you really hard numbers, but now you get a calculator? And so it's like a trade-off. But for some reason, people really prefer having a calculator, even if I give them grosser numbers. So I don't know. Wait, can we do a quick poll? Who would rather have a calculator, but I give you harder numbers, versus I give you really easy numbers, but you're not allowed a calculator, so you have to do all your math by hand? Okay, calculator people. Okay, non-calculator people. Whoa, okay, that's interesting. I feel like when that was a very biased like question. Like I led that like in a very like direct way where I was expecting that outcome. But anyways, okay. I might still allow a calculator on it, and I might still make the numbers hard. Undecided. Okay, cool. Okay, let's convert this now to, hopefully you all, in that time you pulled out your calculator and you converted this. Does anyone have the maximum clock frequency? Maximum clock frequency, anyone? Okay. Yes. Yeah, 29 point whatever 4 megahertz. Okay. What is that right? Yeah. Are we sure that's right? Or did we get like a off by 10 error or something? Does this look like a reasonable, compatible megahertz to go with nanoseconds? It's always good to just like double check. It's like, wait a minute, like did I do my 1 over the thing correctly? Let's just kind of think about this for a second. So if we were to like multiply these two numbers together, then what number like should we expect as a result? 1. Well, sure. Let's ignore units. So if we took this number, multiplied it by this number, what would we expect? We would expect 1,000 if we had like done our units correctly. That's just like a good kind of double check thing to think about. Because sometimes sometimes I just forget a decimal point or something, and so sometimes I'll just be like, oh wow, like 294 megahertz. That's a really good number. Then I look and I'm like, wait, like is that actually true? Because if I multiply these together, now that's 10,000. So actually it looks like did not like pass my quick little like, did these multiply together and equal 1,000 trick? So that's a good like kind of rule of thumb is like, you should take clock frequency, clock period, multiply them together. And if it equals 1,000, then it means that you've done your conversion correctly. A lot of people kind of struggle with this sort of conversion. So make sure that you're well versed in it. 99% of the time, the delay is always going to be in nanoseconds, and the frequency is always going to be in megahertz. It is very rare that you would see like picoseconds in megahertz, or you may see picoseconds in gigahertz, but even that's rare. Most of the time, you're dealing in nanoseconds. Okay, cool. This is fun. Question.
Sorry, before we move on, could you just scroll down to the register file and multiplication things again?
Yes. Register file. Multiplication. Yeah. And maybe I should have had, whatever, like more ellipses, because this is meant to represent like 6 whole levels of adders, not just 2. Yeah.
Wait, so can we always just assume that shifting them takes no time?
Oh, shifting it by a constant amount, right, takes no time. Because that is done like in hardware. Like if you just say like, oh, we're shifting it to add like an extra couple zeros at the front, then that that passes through like automatically. Yeah. If we had a dynamic shifter, then yes, that would definitely take up some amount of time. Like on homework 3. Homework 3, you have a dynamic shifter where you can pass in a value that you want to shift it by. In that case, yeah, there needs to be some sort of hardware. Yeah. Yeah, just like, yeah, maybe sit with that. Okay, cool. Let's say now, all right, 29.4 megahertz. It's not abysmal, but you show this to your boss, and they'd be like, all right, looks like that's good first step. And you're like, what first step? Like, I've been working on this all day or something. They're like, okay, good first step, although I need it at 150 megahertz. Oh man, okay, like, what do you do? Okay, so if I need this now at a higher clock frequency, I need this at 150 megahertz, what is now my strategy? Yeah.
Is it like pipelining?
Yes, pipelining, right. What is pipelining? You want to give me a definition of pipelining? What's pipelining? Yeah.
It's like putting a bunch of flip-flops in between steps of the process.
Exactly, yeah, I really like that. So pipelining is just putting a bunch of flip-flops in the middle of your combinational logic. So here we have this really long combinational stretch. We have this register file like mux tree, and then we have this this multiplication mux tree, multiplication adder tree, and then finally feeds into this register file, into this register. So this whole thing is very long, so maybe we can split it up by putting in a bunch of registers. So yeah, if we now want this to run at 150 megahertz, then now I want you to think about where we should be putting in the minimal number of stages, like the minimal number of pipeline stages, meaning the minimal number of registers. So spend a minute thinking about that, and then we'll go over it. So how can you pipeline this using the fewest number of stages in order to get to 150 megahertz? So the first thing that I would kind of do when looking at this question is maybe there's a better way that we can just draw out all of the different levels, like logic levels that we have. Because remember, so we have, how many logic levels do we have inside of this register file? Yeah, we have 6 levels of muxes, but then we also have like the clock to Q delay from the register. And then how many levels do we have inside of this multiplication unit? Yeah, 6 adders and then plus 1 mux stage at the front. And there isn't, like, there is complete like symmetry and uniformity across all of the, like, across a single logic level, right? There's nothing different in the delay versus this mux versus with this adder versus this adder, right? Like the delay, the time that it takes for the input to come in and the input to come out will be exactly the same for both of these levels, for both of these adders. So therefore, we could probably redraw this to just be like a single kind of chain of all of the different logic levels, one after another. So I want to do that instead. So the first thing that happens is we have the register file flip-flop, and this will actually be like a bunch of flip-flops. But the most important thing is just denoting that we have, in this level, we have a flip-flop. And then after that, then it comes out into a mux, and then there are actually 6 of these. So I will create these. So 1, 2, 3, 4, 5, 6. Okay, and then what is the, and I'll denote this. So this is the register file. Okay, and then what happens after the register file? What's the next thing? Yeah, right, it's another mux. This mux is the thing that shifts it, okay? And so we will now just create another mux. Okay, and then what happens after that? 6 adders, perfect, yeah, cool. Okay, so let's now take 6 adders. Five, 6, Okay, and then what is the final thing that happens?
Flip-flop.
Yeah, a flip-flop. Okay. Yeah, that's good. Okay, and so this whole section right here, this will be the, yeah, multiplication. Okay, and if we want our design, what clock frequency did I say we wanted our design to run at?
150 megahertz.
So we need it to run at 150 megahertz. What is the clock period of 150 megahertz?
6 and 2/3 of a second.
Yeah, something like that, right? So if I do, you can convert by doing 1 over 150, and so, and then whatever, multiply that by 1,000. So that gives you, yeah, 6.6, 6.7-ish nanoseconds for each one of your stages. So that means that to create a, to pipeline this, every stage cannot take any longer than 6.7 nanoseconds. And if it does, then that means that we need to add in like more pipeline stages. So let's double check that. So, okay, I will write that out. So that means that, yeah, I'm gonna shrink this a little bit so we have more room. Okay, clock period is 6.7 nanoseconds. Okay. Maybe the first thing I would do is like maybe look at the end, right? So we have this flip-flop here. Well, if we want the minimum number of pipeline stages, then let's see how many like cells we can skip before we like need to insert another flip-flop. So okay, so far we have a flip-flop here. Do we need to put a flip-flop at this stage right here? I think so, yeah, because like if we had skipped this one, and if we put it here, then now we would have the clock to Q delay, which is 400 picoseconds. Then we would have two adders added together, so that would be 10 nanoseconds. So that would be, in total, that'd be whatever, 10.4, then plus setup time, so I guess this whole delay right here would be 10.7 nanoseconds if we had put our register file, or if we had put a register stage right there. So unfortunately, we cannot like skip a logic level here. It looks like we must insert a flip-flop right here. And when we put a flip-flop at this step, then what will our new like total latency in this stage be? Yeah, I think it's 5.7, right? And is 5.7 less than 6.7? Yeah, we're good. Okay, cool. So therefore, it looks like every single one of these adders is actually, unfortunately, gonna have a flip-flop on it. Okay, but then right here, so we have this adder. Well, it's not super clear whether we need to put a flip-flop right there. Would it be okay if we put a flip-flop right there instead and we included this mux? Yeah. What would the total delay from this flip-flop to this flip-flop be if we set it up like this? Yeah, I think it'd be 6.2. Yeah, where you have 5 for this adder, and then for the flip-flop, you would have clock to Q on this side, and you would have setup on this side. So that'd be whatever, 0.7, so 5.7, and then plus 0.5, so that would be 5.2 in total. Okay. Well, could we move this over now by 1? So if we move it over by another 1, then that means that we would add another 500 picoseconds, and that would put us now at, I think, exactly 6.7 nanoseconds. That's a little bit too close for my liking, so we'll bring this over, because yeah, if we had this, then this would be like exactly 6.7, and yeah, maybe I don't like that, how close that is. So okay, so let's put a flip-flop right there instead. Okay, and now, so we have this flip-flop traveling through all of these muxes into this flip-flop. Will this be valid? Is this okay? I think this is okay, right? So we only have 6 muxes, like this whole delay, we already calculated this to just be 3.4 nanoseconds. So this whole time, so this is totally good. Yeah, so in total, how many pipeline stages do we have?
6.
Yeah, so we have this one, so 1, 2, 3, 4, 5, 6, 7. So it looks like we would have 7 pipeline stages in this. I guess it kind of depends on how you count them. Like maybe you would say that this is not a pipeline stage or something. I'm going to say this is 7 stages right here. And we would have to insert 1, 2, 3, 4, 5, 6 flip-flops. Cool. Okay. Good. Makes sense? Yeah. Yeah.
Could we make it like the speed a little faster by moving that leftmost flip-flop one to the right?
Yeah, absolutely. So yeah, great point. So so we know that this runs at 150 megahertz. It satisfies that. What is the maximum clock frequency now that this circuit can run at? What is the longest possible delay?
6.2.
Yeah, I think it's 6.2. It's just the delay through like one adder plus this flip-flop clock to Q in setup time. So what is now the maximum clock frequency that we could run at if our clock period is 6.2? Yeah, so I think our new like top clock frequency would be 161 megahertz. Point 3. Yeah. Yeah, question.
Sorry, why does putting like a flip-flop between everything make the period shorter?
Yeah, because all we care about in determining how fast our clock can go is whether or not we will get our data to each like flip-flop on time. And so by inserting a flip-flop a little bit earlier, now we are shortening the combinational delay. So now we don't need to like wait as long for our circuit to like propagate all of its values and propagate it to the next flip-flop. So now, yeah, we are able to kind of like divide our combinational logic in half. And now, I mean, this does mean though that now this is going to take several clock cycles in order to actually calculate this problem that we were given. It takes multiple clock cycles to do that, but now we can at least run our clock a little bit faster. So now other parts of our design don't also have to run slower. It's like if maybe something else in our design needs to run at 150 megahertz, so we were given that constraint. It's like we must design this circuit to run at this clock frequency. Yeah, so therefore the only solution is to add pipeline stages. That just shortens the combinational delay, and that will get rid of setup violations. Yeah. Okay, wait, so if our clock frequency is now 161.3 megahertz, what is now the maximum clock frequency if we were to now reorder some of these pipeline stages? Yeah, I mean, could we speed up our circuit at all if maybe we add like another like flip-flop right there? Would this speed anything up? No, I don't think this would speed anything up. Why would adding a flip-flop right here not speed anything up? Yeah.
Because like our longest delay is still with those adders, which you can't split up. And then the period over there is like already less than that longest distance between the adders. So adding it is really short.
Exactly, right. So you kind of have to be strategic about where you put your flip-flops when pipelining your design. In order to actually speed things up, you can only put flip-flops on your slowest path. And because when calculating your clock max frequency, the only thing that matters is whatever your slowest path is in your entire design. Whatever your slowest path is going to set your clock frequency for everything else. And so right here, this was not our slowest path. So by putting a flip-flop here, it changed nothing. Yeah, unfortunate. So let's not do that. But yeah, can we reorder now these flip-flops to increase this clock frequency at all? Yeah.
If you move the leftmost one
Uh-huh.
To the right, so all the boxes are together.
Sure.
I think you can make your clock period just 6 nanoseconds instead of 6.2. So you'd save you'd be like just that teeny bit faster.
Yeah, I think you're totally right. Let's double check that. So if we now move this flip-flop over by 1, then what will the delay through our longest path now be? Yeah, let me pull it back up. So it would be 5 nanoseconds plus now clock to queue plus setup. Because now we don't have to also factor in this mux. So therefore, our longest path is now 5.7 nanoseconds. And so now what is 5.7 nanoseconds converted to a clock frequency? Yeah, so now we have just sped up our design even more to 175 megahertz. Yeah, just by reordering our pipeline stage. Okay, cool. Making sense? Feeling okay. A really kind of cool thing though that Verilog tools will do. So, yeah, just by reordering the flip-flops, we got a massive increase in performance. It actually turns out that most Verilog tools will do this automatically for you. And actually what you could do, what you are allowed to do is actually, like in Verilog, you can have like this big circuit right here. And don't do it on your assignments, but I think you might learn about it in 125, the advanced Verilog course. But what you can do actually is you can take all of your flip-flops and just, for fun, you can just kind of like put them all right next to each other. You can just put them all right here. So you can just grab them all and put them all at the very end like this. And so there we go. So we have all our flip-flops right here. So this is whatever, 6 whole flip-flops right there, all in a line. And so you would think like, oh man, like this is the worst possible design. It's like we have all this combinational delay, and then it feeds into like this really fast part of the circuit. Well, actually, due to a algorithm called retiming, so it's called retiming, the tools will automatically figure out how to evenly distribute out all of your registers to minimize your clock period. So just by default, so oftentimes like if you look up like certain IPs, IP meaning intellectual property, so if you're looking at people's Verilog code that they have written with a large pipeline in it like this, it'll be kind of funny because you'll actually just see like a bunch of like flip-flops at the very end, and you'll see something like in a comment. It'll be like, assume flip-flops will be reorganized with retiming flags enabled. And you're like, oh, like, okay, so you're just like kind of lazy, like you didn't figure out exactly like where to put each of these flip-flops, you just threw them all at the end, and then you're leaving it for your CAD tool to figure out. Yeah, kind of fun. Yeah.
In that scenario, do you still have to figure out how many registers you need?
Sure. Yeah. So yes. So you would figure out how many registers you needed, but you could probably make this like a parameter too. So you could quickly check. Yeah, like what? You could just you could say like, oh, I want this to be like a 7-stage pipeline or something. And you're like, oh no, this isn't running fast enough. Let me just increase this now to like a 16-stage pipeline or something. And then now it'll run a little bit faster. And you're like, great, like I didn't really need to care about how to actually distribute it because my tool did that automatically for me. Yeah, question?
And the retiming algorithm is something that like the computer does?
Exactly, yeah, yeah. And I think Yosis supports that. I know basically the more money you give to like tool vendors, like every tool, there's like different versions of it. So the more money that you give to whatever tool you're buying, the more likely you'll have this feature. Yeah, there's like 6 different versions of a tool called Model Sim, which is like hilarious, and they all have like slightly different names, but they're all the same thing. And it's just like they enable and disable certain things. And anyways, so yeah, retiming is often like a more advanced feature that you can pay for. I don't know if Vivado or Yosis actually supports them, but yeah, it's a common thing that you will run into anyways. Yeah. Okay. That was, yeah, fun rant. I was going to talk about, oh yes, okay. Okay, I was going to switch gears just a little bit. Yeah, does this kind of whole thing make sense? The idea of inserting flip-flops between logic levels? Yeah, okay. Also, really quick, when I like drew out this one register, how many registers is this actually? Yeah, this is actually 64 right here. How many muxes is this actually? I think this is probably 32 muxes right here, and then this is probably 16 and 8, 4, 2, 1, right? So each of these is like a different, it's representing a different stage in our logic levels, right? So like right here. Yeah. This is a really good model to like think about logic levels when crafting a pipeline. Okay, well, this is great, but let's assume maybe instead of reading from this register file, maybe instead we just fed in these 2 values in directly. Actually, no, I take it back. Okay, this will not be as related as I thought, but it's still a good exercise that I want to talk about. So let's assume that we have a multi-operand adder. So in the multiplication unit, right, we have this multi-operand adder that takes in 64 inputs and then produces the output. So that is how multiplication units often work. There's a lot of different algorithms, but this is kind of most basic. So yeah, let's assume we have this multi-operand adder, right, where we have where we have 64 inputs. And then let's also assume that maybe every single stage of this multi-operand adder also has a flip-flop on it. Like let's assume that it's pipelined. So if we have 64 inputs, then I guess it'll probably take 6 clock cycles. Cycles, close enough, yeah. So you have 6 clock cycles later, it will actually produce the value, right? Okay, what if we now had 63 inputs? Then how many clock cycles would it now take? It'd still take 6, right? What if it was 33 inputs? How many clock cycles would it take? Yeah, it would still take 6, right? What if we fed in 32 inputs? How many clock cycles would it take? Yeah, it would take 5, right? Because the idea is that when you have to figure out the number of logic levels in a tree, you take like the ceiling of the log base 2. But let's look at what it would actually look like if we were adding maybe like 32, sorry, if we were adding like 33 inputs together. So if we have flip-flops, right, with all these adders, right? So a bunch of adders, and then this happens for a bunch of clock cycles. So maybe this is like whatever, 5 clock cycles, and there's one right here. That also has a bunch of adders. Okay, well, what we're probably going to have is a single input is maybe not actually fed into this adder. So maybe most of these adders, right, they take in 2 inputs, 2 inputs, 2 inputs, 2 inputs. But maybe this 33rd input actually is not added up, and instead it is passed directly into this flip-flop. And then on the next stage, then we'll see that that's when this value is actually used, and it's passed into this, then this, whatever, that's passed into this. Yeah. So therefore, we have this wire that goes directly into the flip-flop. But everything else has this delay added here. Yeah, maybe each of these delays are 5 nanoseconds, but here, there's 0 delay here. And if this were maybe coming out of a flip-flop, going through here, then we have this circuit. And this is potentially kind of a dangerous circuit of where you just have a flip-flop that is directly hooked up to another flip-flop. Why is this potentially dangerous? What is the violation we are scared of here?
Hold time.
Hold time, yeah. Hold time. Why are we scared of hold time in this? Yeah.
Because as soon as the clock switches, that will switch. So the flip-flop will switch its output, so it won't hold the output.
Right, yeah. So the idea with hold time is that, like, yeah, so we need to have set up the value for a certain amount of time. But when we get a clock pause edge, there's some amount of time that we need to have held the data for. So maybe like after the clock edge, maybe we have a hold time of, let me resize this quick. Okay. Let's assume we have a hold time of 0 nanoseconds. And let's assume a clock to Q of 100 picoseconds. So in this case, will we have a hold time violation? So hold time is saying, like, in relation to the clock edge, it is like how long, like after the clock edge, that the data needed to have been held for. But if we have a hold time of 0 nanoseconds, then it means that we don't need to hold it any longer than the clock edge itself. And the data takes at least 100 picoseconds to arrive, so we're good. So this hold time was satisfied because we didn't need to hold it for any additional time. But if we now made the hold time be 200 picoseconds, so this is saying we need to have held the data steady for at least 200 picoseconds after the clock edge. Okay, so we need to have held it for 200 picoseconds after the clock edge, but our clock to Q is only 100 picoseconds. So that means that this comes out after a clock edge, and it arrives a little bit early. How early did this arrive? Yeah, but it arrived early by 100 picoseconds. So therefore, maybe on this end, it didn't have quite enough time to like charge up correctly and send everything through. So this would be considered a hold time violation because the data arrived too soon on this end and screwed up whatever happened on the previous cycle. Yeah. Okay, so how do we now fix a hold time violation if we are currently failing it by 100 picoseconds? How do we make it so that the data doesn't arrive here too early? What do we do? Tell the person next to you, how do we fix a hold time violation? How do we make sure that the data doesn't arrive here too early? All right, what do we do? Yeah.
Make them equal to each other?
Say it again?
Make them equal to each other?
Oh, so unfortunately, we are not able to change either of these parameters. These are just given to you by your PDK designer. So we can't do that. Yes?
We need to put something to delay the number to like straight just going into the flip-flop. So could you do like an adder with +0 or something?
Yeah, you could do an adder with +0. I think that there's probably something else that we could do that's like not a full, like adders are kind of expensive. But yeah, absolutely. So we would definitely want to add some additional delay here. And if we add additional delay, then now, even though the signal changes like right on the clock edge, it actually takes still a little bit more time to arrive over here. So by this time, it should be done charging, it should be done sending over its data, so we'd be all good. So how much delay do we need to add right here? How much delay? Wait, I can't hear you. How many? 100 picoseconds, exactly, yes. So we would want to put a 100 picosecond delay right there. Let's say that we have an inverter. Let's say inverters have a delay of 100 picoseconds. All right, what do we do? Can we use this? I think we can use this. How do we put it here? Yeah.
Just put 2 inverters after each other?
There we go. Yeah, so we put 2 inverters. And so now the total combinational delay will increase from 0 all the way up to 200 picoseconds. So now we will arrive 100 seconds after the hold time has already finished its thing. So in the end, now if we insert 2 inverters right here, then yes, then we pass. And and notice it has to be 2. If we put 2 inverters one after another, this is called a buffer. So if you ever see anyone talk about buffers, a buffer is just 2 inverters. Question.
Are inverters the most efficient way to add combinational delay?
Generally, yeah, I would say so. There's, yeah. Any other questions? No, good? Okay. Great. Yep. Thank you so much, everyone. I will see you on Monday for a review session.